We should start at 2:05. We're very pleased to have Dr. Nader Mirabolfathi from Berkeley. He's a collaborator on CDMS, the cryogenic dark matter search experiment. He's going to tell you a little bit about CDMS and a lot about what we have been working on collaboratively.
Okay, thanks, HEPEC. This is a pleasure to give a talk after our last visit here. I'm going to speak today about the large mass and our efforts to reach very low threshold for dark matter detection or neutrino proton scattering detection. So basically, what are the challenges of producing large mass detectors with thresholds very low? And by the way, I apologize if I sit. I didn't get enough sleep last night. I'm going to, I was told that I don't need to go through dark matter, problematic, and in Williams, etc. You have had a lot of seminars on the topic. But so I'm going to directly go to the challenges of direct detection, and then and the challenges to having direct detection at very low threshold, and then the advantages of the cryogenic detectors, and then I'm going to speak about this effect, Look effect that will help us to lower our threshold detectors, and some inherent form amplification due to this effect. And then I speak about an experiment which is currently ongoing based on this principle. And then I speak about this project limitations and the solutions for these problems that we found here in collaboration with Texas A&M and Berkeley and LBR. And also other methods to lower thresholds. So let me start to tell you that I'm a detector physicist and fascinated with detectors. Let's give a snapshot of the past. We started, at the end of 19th century with this image from one of Röntgen's colleagues, and nowadays, at the end of the century, we have this measurement of the X-rays with the resolutions of about 70.3 eV. If you are not, very satisfied with this, look at this one. We can even reach the full width half maximum of about 3.6 eV. These are the detectors using cryogenic technology, microcalorimeters. And on the other side, you have the first experiments for finding the nucleus, the rather famous experiment, and we are ending with large, huge experiments like Atlas. But so huge progress, but it's not still. We are not at the end. Actually, maybe for dark matter detector, what we need is a combination of the two, a detector of this size with the precision of this size. So with this quick flashback, let's go to the problem of dark matter WIMPs, and it's a very interesting problem in physics. My titles are tough. That can relate, 40 orders of magnitude in the universe from very large, cosmological background to particle physics, and that can relate. Let's say I had a general public talk. I titled it from infinitesimal to infinity. Somehow it connects the two. So, and this is why we have all these searches. There are different methods to search for dark matter. Either you look for the products of annihilation of dark matter in the center of galaxies, center of sun, or other large astronomical objects, or you try to produce them in LC, or you directly try to measure them via the elastic scattering of the nucleus of the target materials on them. And this is where I'm specialized. So if WIMPs actually, as a candidate, as a very plausible candidates, are dark matter, they form a halo around our galaxy, and with the isothermal Maxwell-Boltzmann distribution, the scale velocity is 680 kilometers per second, and the density of 0.3 GeV per centimeter cube, and the V0 of the sun of about 2,230 kilometers per second.
So this is at the sun. These are these numbers.
These are the solar system. So Witten predicts interaction with the nucleus of material, particularly with the nucleus, and if there is such an interaction, what we find, our estimates show that this kind of interaction are very, very rare. We are speaking about a few tens of kV, very rare. This is from an old slide I have. This is much lower. It's 0.1 event per month per 100 kilograms. And for the energies scale of interaction is about 10 keV. So right away we see the challenges of such experiments. Is that you are looking for a very low rate at very low threshold. So here I'm showing some, more different, the event rate, integrated event rate. The x-axis here shows you the threshold of experiment, and the y-axis tells you what is the event rate, total event rate above threshold that you expect from the material. So you can see for 100 GeV, this is for 100 GeV waves and cross-section of 10 minus 45. So different material have different event rates based on their nuclear structure and also atomic number. Because if it's a coherent interaction, you are expecting the factor a squared boost in the interaction. But if you go to lower masses, you see that the event rate, the total event rate will go down and the threshold above 10 keV. Like for example, if you have an experiment which has a 10 keV threshold, you basically don't see it for a GeV, 10 keV, and let alone the masses below this. Because the effect comes from the fact that it's elastic scattering, so you have the m squared, which is the reduced mass factor in the interaction, and therefore rapidly the event rate goes down as you lower the mass, as the mass of the waves goes down. It has one advantage though, is because this is clumping at lower energy, all the backgrounds, if you have a flat background over there, it's like you're filtering, your bandpass filtering at very low, because for those who are familiar with electronics. So if you imagine that you have a large bandwidth and low bandwidth filter. So it is interesting, if you have a very low threshold experiment, then the possibility of detection becomes very high because of this. So it doesn't.
Does the structure matter of these atoms, whether it's a solid or a liquid?
There is a form factor, we say. The form factor, so we extract things based on the shell model of the nucleus, and that can affect your coherence and non-coherence. Yes.
Factors of 2.
Yeah, you see, for example, at certain energies, the event rate can go down to 0 and come back up.
Oh.
So yeah, it can go because
So it can
the
make a big
coherence.
difference.
Because the coherence, you basically integrate over the.
Right. Okay.
Basically, it based on the Debye wavelength of the recording.
Right. So whether you have a solid state device or a liquid device makes a difference.
Depends on the density. It's not coherence at the scale of the gas. Coherence at the scale of the nucleus.
Oh, so then it shouldn't matter very much.
The nuclear structure matters, not the crystal structure.
Right. Okay, that's what I was asking.
Okay, so the challenges, surge sensitivities we want to reach at the moment are lower than 100, lower energy region below 100, far below 100 kV for the recoil. And current limits are about 10 to minus 3 event per day. What you want to reach for next generation experiments is 10 to minus 5 events per kilogram per day, another factor of 100, increasing our sensitivity. And I'm giving here some typical activity of human activity and environmental activity, and you see that with simple shielding, it is difficult to reduce the background to the level of our sensitivity. So an event-by-event discrimination is very useful. Also, you need to have a very large detectors to increase the exposure, and a low threshold and excellent background protection. So
what are we typically decaying? Sorry,
here,
no.
It's
As human
10
decay has
kilograms.
10 to the 4 as
yeah,
10,000
this
decays
person.
per. What's decaying mostly in our bodies?
Potassium, for example, is one of those. And some sodium.
You drink, you eat bananas, and.
Yes.
So that's why I need bananas, is because I'm decaying away. Clearly not decaying away quickly enough. That's where I'm putting my bananas.
If you eat them, you shouldn't go close to the experiment.
What?
That's the rule.
So I'm not allowed to close to the experiment because I'm.
So the expected rate is featureless too. That's another problem, as compared to the accelerated. Being featureless, basically very simple exponential, so it's very close to the background. So I'm giving a comparison also of the challenges to the LHC, like the event rate, the background event rate of 29 per second and 10 events per minute for the signal, and then there the challenge translates to the trigger, trigger of this. So the same problem also, and the same technique that we are using for detecting dark matter can apply to detection of coherent neutrino scattering. It's standard process, standard model process, which hasn't been detected, which is interesting. and it has, once detected, it can have a wealth of information about, like, for example, because it's a neutral and is independent of flavor, so you can, there are many experiments can be based if you have a total rate of interaction. Also here, you see that the cross sections, which is energy dependent, is pretty large compared to what we reach at the high mass beams. But nobody detected them because the energy of recoil for the 3 MeV neutrino is very low. It's below 500 eV. So if you want to reach, if you want to detect any of them, dark matter low mass, or Coherent neutrino scattering, if you have a very low threshold detector, large mass, then bingo, we have the answer for both. So the same detector can be used for the same for the dark detection. So now let's go to the standard measurement we do in nuclear physics. After interaction, you can either measure WIMPs. After interaction, you can either measure the ionization, scintillation, or phonons, and each one of them has their energy to quantum excitation efficiency. As you can see, the phonons are the maximum because the quantum excitation for phonons is very small, it's microelectron volt compared to electron volt to produce ionization, and about 100 electron volts to produce scintillation in, for example, xenon. Measuring one is not enough. You cannot discriminate events just by one measurement, because all you do is measuring energy. In order to discriminate between electron recoil and nuclear recoil, because WIMPs are mainly interacting with the nucleus, to discriminate that, you need to combine the two. And these are the experiments that are called the simultaneous measurement of two parameters, like the Cdms Principle, or otherwise using the combination of ionization phonon. You heard about LUX, and the other group, LUX group, the late James White, and using this ionization and scintillation, and CREST using scintillation and phonons. So CDMS is using the experiment I'm working in, is using the ionization and phonon discrimination. So here you see that the background and signal can be distributed among two different populations that can distinguish based on ionization. I'm going to speak a bit more in detail about that. So now measuring the phonons. There are two ways you can measure the phonons. One way is to measure the temperature. The phonon is, you look at the distribution of phonons after interaction. You produce a bunch of phonons and they go to equilibrium. What you measure is the temperature change in the crystal. And here I'm giving an example that to show you that it is not crazy to think about a 10 keV interaction raising the temperature of a 1 kilogram germanium detector to a level, to a measurable. So what we use is a fact that the heat capacity of the crystal falling into the bipede decreases as a TQ. So at low temperature, if you go from 300 Kelvin, for example, to 20 millikelvin, or 0.02 Kelvin, you gain a factor of your heat capacity will reduce a lot from 5 to 10 times 10. Then we can estimate what is a 10 keV, what does it correspond to energy, just delta E over C, you measure the temperature, but still the amount of, the change in temperature is quite small. But what you are going to use, you're going to use very sensitive readouts, like a squid amplifier, and very sharp phonon readouts, and then very sharp transition edge sensors, where a slight change in the temperature produces a big change in the resistance, and then combining that with a low noise amplifier, you can have excellent signal to measure. I'm sure you hear a signal of an order of 40 nanoamp and the noise of 1 hertz. So very good resolution you can expect from this. Actually, as I said, in my first slide showed these detectors provide the best resolution available at this time for particle detection. So Cdms Principle is basically measuring ionization and phonon in germanium detectors. So you take a piece of germanium and you have a sensor, phonon sensor on it, and you add ionization. So, and what you do, you measure ionizing power per event. And here I'm showing the distribution of events. The y-axis is showing what we call ionizing power, ionization yield. The horizontal axis showing the recoil energy. So you have two populations, the electron recoil, which are centered around 1, and nuclear recoil, where we believe that WIMPs reside, if they are there, around 0.3. So you see that two populations are very well separated. You may say that, okay, you just need to define your signal region and remove your neutron source. Here is a neutron calibration, the neutron source. You just remove the neutron star and start counting. In fact, the problem is that we have all these events that do from the electron report to nuclear report region. So these are problematic events because they can, these are events basically that they have a reduced ionization connection and they can leak to our signal region and destroy our electron recoil versus nuclear recoil discrimination. So we know what they are. These are actually electron recoils which are happening very close to the surface of the detector. The part of the charge is back diffused to the electrodes and then they are not drifted through the crystal and therefore you don't measure it. So CDMS solution for that is to, instead of measuring the temperature as a phonon measurement, you measure the phonons before they reach equilibrium. So let me make a quick cartoon of what I mean by that. Is that after an interaction, you have a large population of high energy phonons produced. And these phonons, as they travel, they decay to the lower branches energies. And as they decay to the lower branches, their mean free path becomes longer and longer. At a certain point, their mean free path, because this decay process is very fast, their mean free path could be so long that it's comparable to the dimensions of your crystal. At this point, we say that the phonon is ballistic. And this happens very fast.
Phonon is what?
It becomes ballistic.
Ballistic.
The energy ballistically goes from point of impact to your sensor. So if you have a very sensitive sensor that can count these phonons, these low energy phonons, then you basically not only have the information about the energy, because the energy is carried by these phonons, but also you have the transients of the phonons, and therefore you can reconstruct the history of the event, including this location. So this is what CDMS uses. And here's an example of all CDMS detectors, CDMS 2 detectors. And one face of the detector is fully covered by a thermal phonon sensors with a very sensitive transition, HSL constant transition sensors, fully covered, directly deposited on the detector. The other face of the detector is the ionization vectors, and it is divided into one inner electrode and an outer electrode to also veto the events which are on this periphery surface of the detector. Here I'm showing the same ionization versus phonon, ionization yield versus recoil energy, and with all these near surface events. But as you can see, that the events, but here I'm plotting it against versus the timing parameters of the phonon sensors. And you can see that these events which were drooping from electron recoil to neutral recoil now appear at different lower timing. So if I cut out all these events, I just remove all the near surface events. So that was very efficient for CDMS2, for the size of CDMS2, but we found that there is a limitation to that, and we decided to have a new design, and the new design of CDMS is using actually the ionization itself to detect if an event is near surface or in the bulk. And the way it is designed, you have ionization electrodes and the phonon rails are interleaved on the surface. So imagine that you have plus and zero ground, plus ground on one side, minus ground on the other side. In the bulk, you see the average of the voltage on both sides. So in the bulk, the field is uniform. And event happening here, electron holes will drift toward the electrodes, and you have because both ionization electrodes on both sides are instrumented in the readout. So you measure two charge signals on both sides. Now, if an event happens close to the surface, I'll make a zoom out and zoom in of this. And if an event appears here, because of the high fields, tangential fields on the surface, the electron holes will be collected only on one electrode. So by looking at the distribution of the charge between the two electrodes on top and bottom surfaces, you can discriminate the near surface and the front bulk. And here I'm showing an actual calibration. So this is one surface charge versus the other surface charge.
Can you go back to the... So essentially what you're... No, one more. So what you're essentially doing is getting rid of the black using another measure. Because what you're really worried about is not the stuff in the bulk, it's the stuff that's bleeding out towards large time.
Yes.
Because you're cutting out a huge chunk of your...
These are the same events. Do you remember?
Yes, because it's right. It's all the stuff above basically a half a microsecond.
Yeah, about half a microsecond. Yes.
because that's where you're.
That's where, because I know that these events, the events which are close to surface, they have different timing parameters, shorter timing parameters. And the reason I can do that is because I'm measuring thermal formats.
Okay, but the question then is, in some sense, what's making, the ones that are killing you the most are the ones that are coming late.
These one.
Yeah, those, and not the early stuff.
Yeah, so we set the cut. So
I know, but that's the previous analysis. Is in some sense, what's causing them to come late, what you're getting rid of with the new design.
What we are getting from the new design is basically all these events appear like only on one electrode. So all of them. Any event which is closer than 1 millimeter to the surface will be collected only on one charge electron. So let me show you the result of the calibration.
Yeah, what I was asking is, what's the difference between the ones in the bulk, which are down less, mostly less than 0, and the ones that are above
This one?
a half? Yeah. So the black is.
What's the difference between these and these?
No. So you have the bulk there.
Yes.
Right, sort of below below 0 mostly.
Below 0. Okay.
Right, but to go up. Right. So that's your bulk. Right,
No,
below,
that's
between
surface.
0.4 and
Those are
0.8.
all the black events are surface events.
I understand, but that's the bulk of your surface events.
That's the bulk of
The
my
question is, what is of the surface events that is making them arrive later? Because most of them are arriving before what you're calling 0, but a big chunk are what's coming after what you call 0. So what are the outliers? What causes the outliers?
The outliers, I mean, we don't really know. But the reason for outliers is not very clear to us.
So the hope is that this new method is just getting rid of all of them, so it doesn't matter.
All of them does not. Exactly, yes. And it's much more efficient.
Oh, of course. Right, because if you can get rid of them, you get that whole, you double your ability to go into the
Yes,
blue.
but not only that, but also that you still have the thermal phonon time cut, so that adds to it. Okay, so without losing that much efficiency because they're correlated. So this is the calibration data, surface events on one side detected, so we reject them and we just keep the events which are equally collected on both sides. In addition to being to reject this geometry that allows us to reject this electron, the surface electron, but you have phonons sensors on both faces of the detector, and that also help us to identify both timing and the relative amplitude and timing between the phonon sensors to identify events which are very close to the surface. So it has two areas. This is a picture of the design, 625 gram germanium, and Texas A&M already fabricated many of these pictures and showed the process actually impressive. Cdms success. So let me briefly go through CDMS strategy and detector evolution. That's it. So we started with CDMS 2, 250 gram germanium detectors, and we ran 5 towers of 6 detectors each, and detectors ended. Now we are running with this new design, 600 gram germanium with the IZ, what we call IZ geometry, and we have 5 towers of 3 detectors each, currently running at 3 now. And for future, for the G2 generation 2 dark matter searches, we are proposing superseding a snow lab. We want to go to snow lab experimental site. Also, we are using detectors which are larger. And one of the reasons we go to larger detectors is because of surface to volume ratio and also fabrication mass. And these are the phonons, and then we also want to probably mix germanium and silicon, because silicon, depending on where the threshold is, the silicon might be more sensitive to the low threshold. So we are going from 100 kilogram to 9 kilograms, so each time we have a factor of 10 at least. What is important in CDMS is that each time we run this experiment, we were background free. It's very important. So you can always increase your exposure, but you can also increase your background. CDMS strategy was to keep, at least at the high mass region, about 10 GeV, to keep the experiment background free, and therefore your exposure and your sensitivity very limited. So, here is the status of many experiments in the field. This was according to the Neutron cross section, and here are cross section. So, plotting the y-axis. So you see this super CDMS. Current super CDMS result. In particular, I want to point you to the CDMS Lite, which is, let's say, a child project of CDMS. I'm not going to explain it more in detail, but which shows at the moment has the lowest sensitivity to low energy weights, the best sensitivity to low excluded gang. But let me go back here. I want to also speak about this super CDMS silicon and germanium high voltage. And as you can see, they can reach, among all the experiments proposed, they can reach at low energies, they are most sensitive. So basically, what we think is that the low energy, low mass winds, and at low energy recoils, the cryogenic detectors are best detectors at So let me go back to this CDMS light. The basis for CDMS lights is what we call the negative loop effect or amplification. So let me explain it. So because it's very important for the rest of the talk, which is actually the second part of my talk, is when you have an event in the detector, you have the phonons produced by the impact, and you collect them on the sensors. But also, as the electron holes, they drift through the electric field. They scatter on the impurities, and they produce secondary phonons. And then you measure those phonons as well as the initial phonons. So basically, it adds. Think about you in a resistor. This energy actually adds to your recoil energy when you measure the total energy in your phonon. So that the amount of energy in loop phonons, what we call the loop phonons, is proportional to the number of electron holes produced and the bias voltage. Think about VI, P is equal IV in a resistor. Okay. And therefore, basically what it is, it's a phonon measurement. If you have a very, very large V bias, it's basically a very precise measurement of the ionization. It's proportional. This is a bad effect for when you want. This is not very useful when you want to do discrimination. It's actually annoying and annoys us. You have to subtract it because it doesn't help you to discriminate as it is proportional to ionization. But if you give up on some discrimination in electron recoil and nuclear recoil because of your low background conditions, you can think of it as a very precise measurement of the energy. Because you have the best of both worlds. Is you can deliberately increase the bias, and you measure phonons, and you measure your signal via phonons, which are low noise increase. Okay, so signal to noise can go indefinitely, and you can actually reach the ionization factor, limited resolution. So here I'm showing you some plots from Holmuk. The first we measured them, and CDMS light actually is an experiment which is based on this principle. So it ran one detector, 6 kilogram day exposure of one of the super scan detectors, and used the phonon amplification for, but was limited to only 69 volts bias. Due to low frequency noise, it has a 14 eV electron equivalent of resolution, which is phenomenal. But because of some noise in the system, like interference and so on, it was limited to 100 eV DAC threshold and 170 eV threshold. But however, so here you see the spectrum of the germanium, of the low background data spectrum, and you see the germanium activation lines at 1 kV and 10 kV, and the limit by CDMS line. So the reason it can go low, although it is background limited, because we have all these factors. Okay. So yet it gives much better limit of sensitivity than the experiments with discrimination. So that's very interesting because this is where again low threshold becomes important. So why CDMS light was limited? Mainly crystal burn. We find that as we increase, so as I said, we can increase the voltage as we wish, but at some point we are limited. In this detector particular, we are limited to very low 60 volts. And above 60 volts, the detectors start to leak. If the detectors start to leak, then you don't gain anything because you are adding noise as you're adding signal. So, but still, this volt across 2.5 centimeter corresponds to only 40 more 4 volts per centimeter field. Compare it to the standard germanium spectrometer. You usually in the standard operation you run them at 1,000 volts, 500, 600, 700 volts across because you have a depleted detector. So very low compared to that. So we were intrigued. Why the Cdms detectors, they break down at such a low voltage? And this is basically the understanding this very low voltage breakdown was the core of what I want to present today as a new results for today. And if you can improve it. So this is a collaboration. I actually get some funding from UC System and RPI and behind that a collaboration between UC Berkeley, LBNO, and Texas A&M with Dash. So the question is, okay, again, why this breaks? What are the causes of the breakdown? Can we have injection of carriers through the electrode, or can the breakdown? Can we have an avalanche, or tunneling? If you have very large fields, you can think of tunneling between the valence and the conduction band directly in the crystal. So the question was that is that because of impact ionization on impurities, leakage to electrodes, conduction over detector free surface, or all these questions we want to answer because it is very important. If you can increase even double, imagine that each time you double the voltage, you double your improve your signal to by factor of 2, which is very important in terms of the if you look at this event rate, if you go back to the event rate of expected event rate of winds. So a factor of 2 in threshold is very low. So so one of the questions we asked, the first question I asked myself, is there a fundamental difference between a 77 Kelvin and a very low temperature detector? Is it the fact that we are operating these detectors at very low temperatures is the culprit in this problem? And again, standard germanium detector, I told myself, why not taking one of these germanium detectors from, for example, Majorana experiment, Neutrino sublimited decay, or Cogent, and run them at very low temperatures, 20 millikelvin. So this was a collaboration. So this is a P-type point contact detectors are.
Say that again. So is the concern that other detectors are doing better, or is the concern that it's because these detectors happen to be sitting at the superconducting threshold?
No, the concern was that, okay, so it's a bit detailed, I didn't want to put it in my slides.
No.
So the detectors, we neutralize our detectors. The difference between our detectors and 77 Kelvin detectors is that in our case, the charge states, or the state of charging of, let's say, impurity is frozen. There is no phonons to excite them. So if you have the charged state, it will remain charged. If it is a neutral state, it will remain neutral until it captures an electron hole. Okay? So what we do in our detector is we neutralize these detectors at the beginning. At the very beginning, before starting any run, we just flash LED photons and we just somehow kind of like shaking the detector until everything becomes neutralized, all the impurities. Now,
But you're still sitting on
you're sitting
on the threshold.
there, but the question was that whether the cross section of let's say carrier interacting to these impurities is different when they are charged or when they are neutral. Like for example, when they are neutral, maybe they have better tendency to release that electron and kind of making an avalanche process. So the fact that the impurities are frozen is that it could be the cause.
There are a lot of photon detectors based on germanium and silicon that were run at liquid helium temperatures, for example, and I don't
Right.
recall such a low threshold for them at all. So
Yeah, this is
really
in some
surprised with this number.
Yes, in some sense, the question is,
Independently
why not
on-
push it way down?
On particle detectors would be similar to the situation there, right? Take germanium or silicon photon detector. They are run at low temperatures, just
And they are
photon counting,
functioning-
but they are functioning at much higher electric fields.
But 77 is too high for us. 77, you're not frozen. That's what he's
I'm not
talking
talking about some, I'm
No,
talking about
for
liquid helium
Yeah,
temperature.
right, and it's like, why not push that in the temperature way below 70, so you're perfectly in the superconducting band? And then all you
Some
do
super-
I'm sorry, just add, the difference is that the 77K detectors have a different dislocation density, which has a higher number of die vacancies. at very close to the conduction band edge compared to ours, where we trap those out. We don't have the.
How about
So looking at the
Coherent?
difference between the two
Right.
it gives us an idea of what the impact will be.
Well, I'm talking about liquid helium detectors, like, I don't know, the terahertz detectors, for example, that are run at liquid helium temperatures. What would be the difference?
Are those depleted detectors? If they are depleted detectors?
I think some of them are.
So that was the question, because if you deplete the detector and you freeze them, then you basically making a 77 Kelvin detector depleted. What we do, we don't want to do that because we want to have, so if you deplete the detector, all of your impurities are charged. Here we want to neutralize because of the way we operate.
So you want both. You need the impurities and you need to not get rid of them. So, that's,
Yeah. So now the question is that, first question was that, okay, let me deplete one of these detectors. Take one of these point contact detectors, and by the way, point contact detectors are very interesting because of the low capacitance and very high signal to noise. And I take one of those, and I just deplete them at 77 Kelvin. And this was a detector which was provided by LBL, a small size of a Majorana detector. And I deplete at 180 volts, and you get, a capacitance of 1 picofarad, which is good, which tells me that I'm depleted. And then I freeze the detector. As you said, I now go quickly to 4 Kelvin and freeze the state of the detector, the charge state of the detector. And then I take the ionization calibration, and I see that there is no breakdown all the way to 400 volts on the point contact. And let me go here and say, because of the point contact geometry and boundary conditions, the 400 volts on the point, on that electrode corresponds to about 6,000, all the way to 6,000 volt per centimeter. So there is nothing intrinsic about germanium operating at low temperature, at very low temperature, because after this, I come now and neutralize it. So I deplete it, totally charged, I freeze it at 4 Kelvin, and go to 20 millikelvin, and then I neutralize the detector. So that means that I freeze it in another charge state, which is neutral, and yet it can handle 400 volts across. So it doesn't break down. So the conclusion of this study was that there is nothing inherent about this. The cause of this breakdown you are seeing is not something that is not a scattering of electrons or holes or carriers on the impurity centers. So that we just ruled it out. There is no problem. So now I come back to you. Yes, 4K, even if it's neutralized, it should work. So there is no problem. So there are two other things. And also, what we measured was the linearity of the neutron gain, because that detector, I glued one thermistor to it at the same time, so we can measure also phonons. As you know, the Cogent or Majorana detector, they don't have any phonon measurements at the same time, but they just glue one. And a thermistor, basically what you measure is the thermal, the temperature of the detector. And then you see very nice linearity. So that's another proof that actually there is 400 volts across the detector, and the amplitude of the phonon signals are proportional to the voltage, applied voltage. Also, what is interesting, this is even more interesting because it tells us that this is the ionization versus phonon. In this integral, I have both measurements, ionization and phonons, but as you can see, they are totally proportional because the root phonon gain is so big that it overshadows the recoil energy, the amount of tiny energy that was called the recoil. But as you can see, as I increase the voltage, the amplitude of the ionization pretty much is constant, but my phonon amplitude increases as I expect. So it behaves exactly as I expected, and it was very good. So there's nothing intrinsic with germanium neutralized. So then the question is, and also if you look at the phonon noise, the phonon noise is constant with voltage. That's another good news, because that's what we wish, is that I increase the signal, I don't touch the noise. That's what it says. My signal is increasing, my noise remains the same. That is my signal to noise equals inherent voltage.
So what is increasing the voltage?
Here?
And what left?
Oh, these are electronic. This is depending on one run versus the other. But the main part is this one, which is it's very much out of our analysis. The filter. Just
And there's the follow-up question on that is, at 4K, you missed the first part, the heat capacity will be too high. So you want to keep the heat capacity low as well, so you can measure some change.
I didn't understand. You were thinking about proposing running at 4K, or you were thinking
No,
about why?
I was just surprised
Yeah,
why
that's
all
right.
detectors
That's right.
run without any
Yeah,
problems.
it's a neutral, there's some I think the 4K detectors are completed.
And I'm sorry I missed the beginning, but what's exactly the state of the detector? So by saying neutralized, what do you mean? What's the concentration of
That,
impurities?
to our best knowledge, all the impurities are not charged.
And all,
The
how
minimum
much?
energy is not charged.
How much? All means, what's the density of the impurity?
Also 10 to 11%.
10 to 12 per cubic centimeter.
No, actually 10 to 11, 10 to 12 is on the high side. 10 to 11. There are many, this detector I measured is about 10 to 11, 5, 10 to 10. So conclusion from the PPC work, the point contact, theta point contact, is that no intrinsic breakdown that we can trace back to the neutralization of the detector. Scattering on neutron is no avalanche observed, and all the evidences actually points toward the electrodes. Maybe there's something wrong on the electrode technology with CDMS. So the CDMS detector, if there is a leakage through the electrode, what you expect, if you think about semiconductor devices, is there should be some rectifying effect, or let's say a polarity dependence on how the electrons or holes go through the crystal, because if that's where the metal is sitting with respect to the detector, with respect to germanium. With CDMS detector, we cannot test this because CDMS detectors, they have metal on both sides of them. So regardless of which polarity you put, one of the contacts sees either of the polarity, positive or negative. So we need to break that symmetry, and that's why I came on our sphere. So, and with the discussions with Rumbach and Rusty, we had a new design. And the idea was that instead of having metal, instead of biasing through a metal contact on the germanium, we put the electrode with a gap. So we leave one surface of germanium bare. Basically, you suppress electron rejection. Okay? And these are and this way you can say if I change the polarity, then either I have breakdown at certain voltage, or I don't have a breakdown. Okay, so it is instrument like this. But the other face of the germanium is fully processed as a standard CDMS detector with a phonon sensor. So you have a thermal phonon without this stuff. And also, because you measure a thermal phonons, you expect much better sensitivity than this thermistor I was talking about in the previous point contact detector. So now, so here is the result. The CDMS detector without the other surface actually can now hold all the way to 400 volts on one polarity. On the other polarity, it breaks down at around 50 volts. So this clearly tells us, and if I'm going to that slide more detail. But the other thing is that again, with a thermal phonon sensor, we looked at only one phonon channel because in the building up the tower, we messed up. So 4 channels were not operational. You look at one phonon channel, and just one phonon channel is enough to look at a breakdown, because if there is any breakdown, you see a noise effect on any of the phonon channels. So these are the 60 kV events. So at 400 volts, 200 and 150 and 0. The noise again doesn't change with the voltage, which is very good news for a thermal phonon measurement. And we have the signal to noise. We estimated the signal to noise based on one phonon channel, and this is what we got. So we get about 11.9 eV electron equivalent resolution. So which to me is the record low for the detection of the size. And this is what only one phonon channel. The next one will operate all 4 phonon channels, and we expect a root square of 4 improvement in signal to noise, which is fact that brings us to 7 eV RMS. This is impressive. So, on the other hand, but this wasn't actually what I was seeking.
That's 1,000 times lower
but it was a
than
bonus we got. Yes.
That was 1,000 times better than our CDMS.
Yes, that's to put it this way, our KEs. So, and now about the polarity, that's what we wanted to understand, and I think we understood now. That the reason there is a asymmetry between let's not asymmetry. There's a polarity dependence of the breakdown. So this is operating detector on positive voltage, and this is operating detector at a negative bias. And by negative, because I'm biasing from the electrode, the phonons on the opposite side, what it means that the electrodes the metal germanium contact has a tendency to inject holes. And this is something, I mean, speaking with one of our postdocs, it's something that I think Russ would agree that this is basically what happens usually with germanium. They pin, the permeable pins, basically, to the low valence band. But we understand that. So for the next round, what we are going to do, we are going to, let me see if I have a slide on that. No. For the next round, we are going to have all 4 phonon channels working, and also what we found is that the gap between the electrode and the detector was a bit too large. We were designing for 1 millimeter, but because of the cryogenic or thermal contractions and expansions, the contractions, they become larger. And what we are going to do, we are going to improve that so that we keep the gap small, so that for the same voltage we are applying, we get more voltage drop across the germanium. Imagine, think about 2 capacitors in series. If you have 2 small capacitors, the smaller one takes most of the voltage.
But
So,
what's the conclusion on the origin, on the mechanism of the low voltage breakdown and the bit loss? Can you summarize it from your studies?
so from this, we think that it's a pinning of the Fermi level in the metal to the valence, or close to the valence band of the germanium. Somehow it opens a highway for phonons to go to. But I think better explanation.
Did you come back and do just a regular low voltage test, go to breakdown, and then come back and redo that low voltage test?
Go to, yes, that's what you do. That's what's here.
No, so you're showing what the breakdown is, but after you've done the breakdown,
Yeah.
come back and do another low voltage test. Did you see a change in your baseline versus?
Not really. No, because this is what I'm showing here is breakdown, and after I ground the electrode, what you see that all the charge that was accumulated up there, okay, acts like a voltage. It actually counteracted the field, and now it becomes like a positive voltage. So this is same data series. It's just grounded during the run. The same thing for the positive. You see that you have all the loop phonon gain, but then it drops as soon as you ground. So nothing major changed because we repeated this experiment always the same. So this was interesting. So we think that we can gain at least another factor of 4. At least another factor of 4 in our signal experience. So I hope that next time we're here for a talk, I can give you an EV threshold.
Is there any Schottky barrier there on the interface?
Yes.
Because you are showing like flat bands there. It would be nice to see actual
Yes, absolutely.
picture of the bands.
Yes, we make it there.
Okay.
I just want to show that. There are other ways also to reduce, to improve the threshold, is to look at the phonon themselves. So our phonons design are not, is not optimized for phonon resolution, because in any case, obviously, we are limited by ionization. In the Cdms standard operation, we are limited by ionization for discrimination studies. So we can optimize our phonon, and first thing is to get rid of this low frequency noise in our phonon response, and we think that it's coming from our warm electrons. Getting rid of it. The most important thing is that our phonon, the phonon energy, time dependence, or let's say signal, is by far smaller bandwidth than our, or let's say longer than our actual phonon sensor pulse response. That means that you are basically losing all this energy. If your sensor, imagine that your sensor is going fast, go up and down, and only this amount of energy is collected. We think that we can slow down our sensors, and the only way we can think of is by lowering the critical temperature of our tungsten transition sensors. And I think Luca also is working on that to see if you can systematically reduce TCs of lower TCs, and we believe that our signal to noise varies as TCQ. And we already have some result from a couple of detectors where we have different TCs, and they follow very well this line of TC. So I think, we don't know here yet, because there are all sorts of things that may happen. Like you have extra heat capacities that add to your phone, like impurities, iron, or something that can contribute to your heat capacity. But the first principle, we should be able to reach, just by phonons, not even loop phonon gain, just by phonon themselves, we can reach this.
In the early slide, you have a nice slide motivated the nature of phonon energy ionization.
I'm sorry.
Early slide, you have a nice slide to motivate the three method to measure.
Yes.
Phonon ionization rate. Then phonon has 100%
Yes.
So you think this is only for checking
For ionization phonon. This is for just phonon measurements.
Right, so that means there is not catching 100%.
Basically, the phonons, it depends on the efficiency. When I said 100%, it's 100% of energy goes to phonons. Now, how many of those phonons we capture? When you actually measure it, when it does, it's something else. We don't measure 100%, but it's 20% maximum.
I understand.
Yes. But the important is that you can scale the energy. The energy scale is very, there's no crunching factor. So that's another avenue, method of improving our signal to noise. And also we continue working on our surface or leakage detector. We also want to study if there's anything wrong with our surfaces in addition to the electrodes. And I think to me more or less it's clear that our leakage is coming from our electrodes. It's an injection through the electrodes. But we, nonetheless, we think also we want to study what is the surface leakage, because for IZIP geometry, where you have ionization and phonons are very close to each other, you don't want to have a leakage at all. And this is by transfer length method that Rustika and Andrew are working on. And this basically what you do is you measure the resistance between any two of these electrodes, and you plot the resistance versus the distance. In theory, it should be linear, except if you have a contact resistance. And then the zero crossing of that tells you what is the contact resistance. And also we can think of using the same method to study if there is a surface breakdown, which would be very interesting concept. So these are the devices that was made by Andrew and designed by Kyle. And for this measurement, you need to have a very good electronics, very sensitive current measurement. This amplifier, which is going to operate totally at 4 Kelvin, was designed with one of our gas units. And the board is already made, the whole board, and the one board is made. So we are expecting to run this one by the end of the year. So with this, we conclude. So the evidence for dark matter only growing. So and the subatomic nature of that is very difficult. Dreams very plausible, and searches for all masses should continue, because we don't. The models predict mass scale, very different mass scales for dark matter. And project detector offer very good signal to noise. It showed because of only if you think about the phonon efficiency, the energy transformation efficiency, or let's say excitation, quantum excitation of the phonons, actually can provide the best signal to noise for these kind of low spectral measurements. And the same technology that we developed for low mass waves can be used to detect neutrinos, neutrino Coherent scattering, which is also an interesting question in standard model, why we haven't seen it yet. I showed that using negative effect, CDMs can reach very low threshold, but we were limited by voltage, and now we understand what is that limitation. I believe that next time, when we run this detector, we can, this 400 volts I was talking about is a magic number, is the fact that in cryogenics, if you have a feed-through connectors, you don't want to put much larger than that, otherwise you burn your feed-through, and then your vacuum starts to leak on that sort of problem. So 400 volts was a limit that was given by our electronic. So don't go beyond that. Otherwise, we have a new fridge in Berkeley that we commissioned for higher voltage applications, and I think with that, plus the detectors that we are getting, we can certainly achieve EV scale, really, truly. And then those detectors can revolutionize the search for low mass waves. So,
the wind can be hiding. Any questions?
Spoken like a real boy.
Never agree. I have to leave quickly, but any questions?
What do you think is the time scale for the next set of results on this class?
Here's interesting. We came here in August. We discussed, and
Is it possible? So let's say this is the right way to go.
yeah. Oh, okay.
Could you put this in? fabricate some of these for Snow Lab?
Actually, simply fabricate these papers and snows.
Will these be in addition to the ones at Snow Lab, or we just make all the Snow Lab?
We still don't know what's, we are designing the fish for 400 kilograms and we are putting 100 kilograms in and everything's perfect.
So there's, that contacts would be highly variable, and the TCE, the expansion differences, there's detector variances in that.
Isn't that engineering? We can think of methods.
It's just engineering.
Just the engineering. Can't we just hire somebody to fix that? What's the limiting factor there? Money.
The point is, given this information, we can now look at different contacts that don't in the Fermi level close to the conduction method.
Yeah, right. The big thing is you now understand what was causing it. Once you know what's causing it, then you can be creative about it.
Exactly.
That's right.
And we can do that from both the materials point of view and process.
My dream is one day if we can have the actual ionization measurements and phonon measurements in a detector having two medium. Let's say if you have a germanium which is operating at low voltage, think about xenon double phase. So the electrons come in low voltage Richard surface. If we can come with an interface that allows the electron to pass through, to go through, and then it reaches another germanium at high voltage. So basically you have best of both worlds. You have ionization, and you don't wash out the information, the recoil energy by this weak phonons in a single detector. So you will have discrimination maybe all the way down to 100 dB, 200 dB. And that is very big change. If you can do that, that's
Surprisingly enough, the solution to this is a dielectric.
Dielectric?
Dielectric.
Yeah, that's what I was.
A very thin dielectric at the interface that removes the Fermi level.
Like
energy,
pigeon poop.
but is thin enough that you get quantum tunneling through the device, no matter what the bias range is.
It's a CMP.
It's actually a simple thing.
This is something, I mean, really, it's really
Notice, what did you use to separate your the electrode?
Oh, yes, that's a good question.
Did you use photoresist or?
No,
Very much.
it's sitting on one detector house. So it's sitting
Oh,
there,
okay,
and it's
okay.
in another detector housing, and another detector housing behind it. And you try to adjust those.
Okay. Now, if
The
you
first try we use Kapton.
Kapton tape?
It conducts.
Well, yeah,
Comes back.
400, yeah, that's nice. But it, say like a thick layer of photoresist, you'll get a nice uniform layer of this. What? Now, depending on how close you want it. So, we're talking microns there.
And the photoresist is very.
I don't know.
Because, it's enough to have electrons. No, if you reach that electron volt resolution, what becomes our background becomes infrared. You should really carefully be careful about infrared.
Any other questions?
Oh, and I liked what you did with that little detector inside the house. It was very cute.
Yeah.
That was something I would do.
Yeah. I did that, then it sites did.
Well, it was-
Most of the Zoomer students did.
Yeah, well, I just saw that and I
presented
was like, yes!
Thanks a lot, man.
Okay.
Very nice.